Okay. Right. Still, again, we are focusing on still on in this material science because as a mechanical engineer, we are going to use a lot of steel. Most of the mechanical component, most of them other than non ferrous alloy. Ferrous is the major materials or metal that are going to use in the heavy engineering application. Okay, so the steel and the alloy steel. Okay, why we all right? The outcome of this course is you need to uh, be able to determine the advantages of using alloy steel compared to plain carbon steel and cite some of its applications. So meaning that uh, we are going to talk about alloy steel, not just a plain steel. You know what is steel? Steel is a iron plus carbon. So now we are going to discuss on the other elements that it being added onto the steel. Okay, and then what is the effects of various alloying elements on the properties of the steel? And you should be able to explain what is merging steel and their heat treatment cycle to produce this steel. So again, when we talk about metal, okay, metal, not ceramic, not polymer, not composite, just metal. Okay, there are ferrous and non-ferrous. Okay, so look at this. Ferrous, we talk about steel, iron, cast iron. Okay, they are the major part of the metal. And when we talk about nickel, aluminium, um, uh, copper, those are elements, is another half of metal. Okay, so meaning that ferrous is the major material. So you need to really understand about the ferrous. So in ferrous, there are steel and cast iron. Okay, we have studied about cast iron, where it is a when we talk about cast iron, there are several types of cast iron. There are 4 types of cast iron. They are different in terms of the composition and heat treatment process. But the steel, there are more on steel. Okay, and then for non-ferrous, yes, we talk about copper, aluminum, and others such as the magnesium, titanium, and nickel. So steel. Now we are going to talk about steel. Okay. In steel, okay, there are 2 categories. One is plain, another one is alloy. Okay. Plain is without other alloying elements. When we talk about alloy steel, is a category of alloy that having more alloying element, not just mixing with carbon only. Okay, so as a recap, plain carbon steel is an alloy. Okay, plain carbon steel. When we talk about steel itself, it is actually an alloy. Alloy of what? Iron plus carbon. Okay, where the carbon is a fundamental constituent and no base of other alloying element is specified. Okay, only iron and carbon. Iron and carbon is interstitial, and then where the small atoms of carbon diffuse into the iron structure, the crystal structure of iron. Okay, some limitation of plain carbon steel are includes uh, it cannot be strengthened beyond about 690 megapascal without losing its ductility and impact resistance. So meaning that the maximum that you can see uh, uh, to um, uh, to the strength is 690 megapascal. Okay, and then one is that criteria. Another thing is if you trying to harden the materials, uh, there's a limit, meaning that you cannot deep harden. Okay, only at the surface only. Okay, so that's the limitation. So remember, we discussed about hardenability just now. As compared to plain carbon steel, alloy steel can be high, not high, alloy steel has high hardenability. Why? Because it has deep hardenable. So it can harden at the far distance from the quench end. Okay, so means that you need alloy steel if you want to make it hardenable. So they have low corrosion and oxidation resistance, so meaning that won't be easily rust. They have poor impact resistance at low temperature. Okay, so alloy steel are iron carbon alloy. Okay, meaning that iron carbon is the basic material and we alloy it with high measures of different alloying elements. Okay, so low carbon, we can have a plain, high strength, or low alloy. But for medium carbon, we can have plain carbon and heat treatable. And high carbon, okay, this is a different grade, different composition of carbon. If you have a small amount of carbon, we call it low carbon. If you have medium amount of carbon, we call it medium carbon steel. uh, High carbon steel is comparatively, it has higher carbon composition. So if you will you have always heard about stainless steel, right? Stainless steel, it is actually high carbon steel, and it's being added with chromium. So it is not low carbon steel mixed with chromium. It must be a high carbon steel and added with chromium, then it will become stainless steel. And other than that, without the alloying element, we call it plain high carbon steel. But if you add some alloying elements such as tungsten and nickel, you can have, uh, we call it tool steel. So it used for tool application. So low carbon steel, okay, the plain without any element, low carbon steel is a category of steel that having carbon content less than 0.25% carbon. So this amount of carbon, it is very difficult to form martensite. So remember, martensite is a structure that having carbon trapped in the FCC structure of arsenide. So without sufficient amount of carbon, so you won't be able to have tetragonal structure, BCT structure of martensite. So there's no way to have martensite if you have very small amount of carbon. So meaning that strengthening is accomplished by only method strength hardening. Okay, co-working. Okay, jangan berangan lah you nak buat quenching, lepas tu you rasa dia boleh jadi uh, high hardness. No way, because it won't be able to be hardened by heat treatment process. Because if you conduct the heat treatment, you cannot increase the strength or hardness because there's no martensite form. Why? Because less amount of carbon. Okay, microstructure consists mostly ferrites, making them very soft. So less carbon. Remember, if you increase the carbon, means you can increase the strength, reduce the ductility, of course. So if you look at under microstructure, it is mostly a bright region of the grain because it is associated with the what we call it ferrite. Okay. Sorry bising saya tak boleh nak buat apa lah. Ada construction lah jiran-jiran. Alright. Okay. Plain low carbon steel. This is example, which is the composition of carbon is very low, which is 0.08. And the it consists of polite. Why? Because 0.08 is larger than 0.02. Okay, less than 0.02, you don't get polite structure. Why? If you still remember, okay, sorry. Alright, for the iron carbon phase diagram, okay, this is example of iron carbon phase diagram. So This is 0.76 and 0.02. So the polite is coming from the eutectic reaction. Okay, so whatever for this composition 0.76, you will get 100% polite. Okay, a lamellar structure like this. Right, so you will have this kind of pearlite structure if the composition of your carbon between 0.02 up until 6.67% carbon. Okay, if you have 0.01%, you won't be able to obtain pearlite structure because it's not passing through the acetylene reaction, which is the temperature 7 to 3 degrees Celsius. So 0.08 is somewhere here, 0.08% carbon. So therefore, you can have a pearlite, but the amount of pearlite quite low, which is at this region. Okay, the darker region, like this one is pearlite. Okay, you cannot see the lamellar structure because it is just an optical image, optical microscope. If you use scanning electron microscope, you can enlarge up until 40,000 magnification, and you can see clearly the structure of a light. The plain low carbon has outstanding ductility and toughness. Uh, so therefore, because of the ductility, so you can easily machine. Okay, so the machinability is high. Okay, and it is weldable and is relatively inexpensive to produce. Okay, they use for making car body panel due to their excellent ductility and machinability. So why? Because if you look at the structure of the car body panel, okay, uh, you need to weld between one structure into one structure. You need to cut it. You need to fit it with other components, such as, for example, the car body, not the frame, but the door panel. Okay, the door panel you need to fit with so many system like power window whatsoever. So meaning that you need to machine the panel. Machine means one of the machine purpose is to drill a hole for fastening process, to fix the system like a power window, locking system, many other system need to be integrated on the car, the door panel of the car only. So imagine that process require machining. So ductility is needed for this kind of uh, machinability is needed. Machinability properties is needed for this application. So to make it easy to be machined, it's require what we call it ductility properties. So the application always related to the properties. Okay, and the process also always associated with the properties. So if you think you need to conduct a machining process, make sure your metal has a sufficient ductility properties. Okay, to obtain ductility, high ductility, meaning that you require low carbon. If you have high carbon, there's no more sufficient ductility for this kind of application. Um, hmm, okay, example, the typical application for plain low carbon steel include structural shape, for example, I-beam, channel and angle iron, the sheet that used for pipelines and buildings. Okay. So for the low carbon steel, uh, uh, low carbon steel, you can increase the strength. Okay, increase the strength. If you add some alloying element, it will become an alloy where we call it high strength low alloy steel. Okay, high strength low alloy steel. Basically, it is the name given to the low carbon steel that having improved in the what we call it in terms of the strength. Okay. HSLA contain other alloying elements such as copper, vanadium, nickel, molybdenum in combined concentration as high as 10 weight percentage, meaning that your existing low carbon steel, the low plane carbon steel is only 90%, and the remaining alloying element is up until 10% only. Okay, so the result is you will have a high strength and hardness compared to the low carbon steel. Okay, why? Because we have add this kind of alloying elements. So because of this alloying element, it can be heat treated. Okay, before this, without this alloying element, you cannot heat treat it, meaning that if you just conduct a heat treatment process, you cannot improve the property. But with this kind of alloying elements, you can improve the properties in terms by using the process heat treatment process. Okay, remember, if we look back to the low carbon steel. Okay, basically, if you have low carbon steel, the only way you can improve the strength is by using strain hardening. Okay, not by heat treatment process. So, but if you uh, apply alloying element, yes, you can improve the strength by heat treatment. So, the alloy elements are intended to alter the microstructure of carbon steel to produce a very fine dispersion particle in an almost pure ferrite matrix. Okay, so there are some depression of precipitate in the ferrite matrix. This is the strengthening mechanism whereby dislocation motion will be impaired through this precipitate. So the white color is the precipitate itself, right? So rather than improve the strength of um, the steel by cold working, meaning that strength hardening, you can have extra uh, dislocation barrier. Okay, so which is this precipitate. Okay, precipitate. uh, so if you look back in the module 4, there's four different methods or mechanism to improve the strength. Okay, there are one is alloying, two is grain size refining, three is strain hardening or cold working, and four is precipitation. So without alloying element in the low carbon steel, the only way you can improve the strain by strain hardening or co-working process. But now by adding up until 10% of weight of the alloying element, you can improve through the precipitation. So to obtain the precipitates, you can have it through the heat treatment. Only by heat treatment, it will develop the precipitates. So the application of HSLA is so therefore the tensile strength is can increase excess of 480 megapascal. It has a higher strength to weight ratio. There are ductile, formable, and machinable. HSLS still are resistant to corrosion. So next is medium carbon steel. So when we talk about medium, so the range is between 0.2 until 0.6. Okay, the amount of perlite slightly increased, but not 100% perlite. Remember, the 0.76 or sometimes they call it 0.8% carbon, you will obtain 100% perlite. So this kind of plain carbon is considered high carbon steel. So medium is between 0.2 until 0.6% carbon. These alone may be heat treated by austenizing, quenching, and then tempering to improve their mechanical properties. For this category, you can have martensite. The plain medium carbon steel have low hardenability. Only thin section can be successfully transformed to martensite upon quenching up until the core level. Okay, fully forming martensite throughout all the media, the volume. Okay, so there are some limitation for this what we call it category of plain carbon steel. So therefore, if we add some alloying elements such as the chromium, nickel, and molybdenum, it can be improve the capacity of medium carbon steel to be heat treated. These alloying elements improve their strength, ductility combination, and also possess a good wear resistance. So if we look at the microstructure, okay, for example, this one is plain without the heat treatment, and this one is a 0.4. Look at 0.4. Unlike the 0.08 just now for low carbon steel, you don't see much pearlite, but for this, without the heat treatment, you can see pearlite structure. Okay, the area of pearlite is quite wide. Okay, and this is a ferrite. Okay, the dark one is pearlite. So now, after quenching, you can see a martensite. The needle-like structure. Yang tajam-tajam tu, itu adalah martensite. As a result of their high strength, resistant to wear and toughness, they are often used for railway tracks, train wheel, crankshaft, gear, machinery. Look at the application. Unlike the low carbon steel almost for static load application, like for the water pipeline, I-beam structure for buildings. I-beam structure, imagine in our building, there's a steel. It is just a low carbon steel. Why? Because it does not involve any dynamic load, accidental load. It's just a static building. Building doesn't exclude, or maybe in Japan, yes, they have a earthquake, something like that. So maybe they don't use low carbon steel. But that one is another story. They have another prevention for the earthquake. They have designed the earthquake prevention in their system. But look at the comparison of the application. Okay, low carbon steel and medium carbon steel. Low carbon steel mostly for the static load, but medium, look at this. Okay, it's a railway track. Imagine there's a train, okay, moving back and forth all the time. So there's on-off load, on-off. It will experience dynamic load. Okay, it will become fatigued after one time. There are cyclic load is being on and off experienced by the railway tracks. Okay, the train wheel is moving part. So there are on and off. There are fluctuation of the load. Okay, compression, tension, compression, tension. Okay, that one is a cyclic load. And then crankshaft, crankshaft tahu kan, in the jet engine, gear. Okay, load is moving. It's a when there is a rotating structure, there is a compression and what we call it, tension load. Okay, machinery part. Okay, these are combining between static and dynamic load, sometimes accidental load. So unlike the plain carbon, you can easily relate with the application. Example, if the question asks you to give an example, it is easy. Static load, give it to the low carbon steel, but dynamic load, give it to the medium or high carbon steel. Okay, this is another example. Another alloying element, another category of steel, okay, which is a high carbon steel, basically up until 1.4% of carbon, must be larger than 0.6, okay, 0.6. And due to high carbon content, they can be heated by quenching, okay, and they are almost always used in hardened and tempered condition. Okay, you will never use high carbon steel without this treatment, because that's one is it is very expensive. It's not easy to produce high carbon steel. So why you want to use high carbon steel if you don't want to achieve the good benefit out of it? Okay, you have invested for the high cost for this kind of alloy, and suddenly you are not optimizing. Basically, this steel is being used as hardened and treated steel. Okay, there are almost right. So you can see that it's contain. This is plain. Right, and on the left side is without the quenching, and on the right side is with quenching. Without the quenching, you can see the white region is quite limited, but the polite. This is ferrite. Okay, the majority of ferrite. This is cementite. Okay, 1.3% carbon. So you can see there are huge portion of perlite, okay, because the carbon is high. And if you quench, you can see a very fine structure um, of martensite after quenching. Okay, so it is contain huge portion of martensite and fine structure of martensite. All right, look at the application. High carbon steel. Uh, it is hardest and strongest, and yet least ductile of the carbon steel. Okay, there are especially wear resistant and capable holding a sharp cutting edge. Okay, sharp cutting edge. Why? Cutting tools. So you know the function of cutting tools, right? Um, it will cut anything, and to cut anything, it requires a sharp structure. So sharp structure, it is very tiny at the end. If it is ductile, it can easily blunted. Okay, so ceramic knife, one example of uh, uh, equipment that utilize the ceramic, which is can produce a hard structure and maintain the sharpness. Okay, so that's the reason high carbon steel is being used for the cutting tools. Okay, because it can maintain the sharp cutting edge. So it can use for the tool stick. Okay, the tool the tool and the die still are high. Die bukan mati. Die is you know what is die? You know what is die? Anyone? Are you still there?
Ya udah.
What is die? Die. Die. Uh, sheet. Dies. All right. So whatever you want to produce a machining process or forming process, there is a dies that give a shape to any final output. For example, like die casting process. Okay. So this is die casting process. Look at this casting process. So mana die dia? Okay, now the example, let's choose one example of drawing process. Okay, so drawing process, for example, you want to draw a wire. Okay, for example, Okay. Um, all right. This is the drawing process where you have the initial size of large diameter wire, and after being drawn, it will become small wire size. Okay. After passing through the dies. Okay. The dies is a structure that will shape your product. This is the dies. Okay. For example, the drawing for the wire. Okay. So these are the dies. Okay. The material of these dies, you need to use tool steel. Okay. So there are different sizes of the initial diameter and the final diameter. You can see on the top of the cavities is a large diameter, and at the bottom is a small diameter. So when you draw the wire ataupun you pull the wire, after passing through this die, the wire will become smaller. So the material to use for the dies must be tool steel. So the tools and die steel are high carbon alloy, usually containing chromium, vanadium, tungsten, and molybdenum. Not just high carbon content, but containing other alloying elements. Okay, these alloying elements combine with carbon to form very hard and wear resistant carbide. Okay, so you know high carbon steel is contain more cementite, which is iron carbide, but in by having this chromium, vanadium, tungsten, okay, the carbon is not just combined with iron to form cementite, but the carbon instead, because there are huge amount of carbon for high carbon steel, so the carbon tends to form a bonding with um, another elements such as tungsten, titanium, and so forth. So this carbide, okay, will uh, giving more strength to the total alloy. Okay, so the carbide precipitates is not just iron carbide. There are another carbide which is tungsten carbide, chromium carbide. So this new carbide is stronger. So the application, these still are utilized as a cutting tool and dies for forming and shaping material as well as in a knife, a razor, and so many cutting tools. Okay, and in fact, high strength wire they use for example, yeah, spring. Sometimes they use stainless steel. Spring materials is a quite heavy duty application, like for the suspension and something like that. But high strength wire. Why wire? Because uh, let's take a look at the application of the wire. Example for the bridge suspension, cable car. All right, it's carrying a lot, heavy loads, and it's formed some kind of load bearing structure, as well as it's experience the static plus dynamic plus accidental loads. So these combination loads um, can um, uh, the high carbon steel can serve for that kind of application. So another category of alloy is high speed steel, when the two steel contain a combination of more than 7% molybdenum, tungsten, and vanadium, and more than 0.6% carbon. Uh, they are referred to high speed steel. Okay, more special. This alloy element increase the heat resistance and durability of the two steel. Okay, so the effect of alloying elements. Okay, this steel you can use for not just tool steel for hammering and other normal application like this one, like a hammer, a cutting by using normal for the hacksaw or this kind of category. But if you cut by using high speed, something like that, so there are another special tool stick which is like this one. um, the drilling tools, high-speed cutting, you are need to going to use this higher performance of uh, steel category. So how actually the alloying element can improve the steel? Okay, so because it seems like we add new element, it increase the properties. Uh, but how actually this element improve the properties? Okay, for example, look at one's perspective, which is hardenability. So carbon control the hardness of the martensite, because no carbon, no martensite, or less carbon, no martensite. Besides, carbon also increase the hardenability of the steel by retarding the formation of pearlite and ferrite. Then, if you look at this, okay, by increasing the amount of carbon for different grade of uh, alloy steel and okay, in this category, they are all same carbon content, but having different alloying elements. So by adding alloying elements, you can improve um, the hardenability of the steel. Okay, sepatutnya ditunjuk. They're supposed to they show some kind of different carbon content, but this one they are all the same carbon content. Maybe another line can be shown here, 1080 for example. Okay, can really show can reflect to this fact, which is carbon increase the hardenability. And the addition of a boron can also significantly improve the hardness of steel, and typically used with lower carbon steel. The element of chromium, molybdenum, manganese, silicon, nickel, and vanadium all retard the phase transformation from arsenite to ferrite. Okay, because we know that ferrite is ductile, and pearlite means martensite. Ferrite and pearlite means that if you retard this pearlite and martensite and ferrites, you can obtain martensite. And besides that, the solid solution hardening, by adding alloying element, it can increase the strength by forming solid solution with ferrite. Okay, they cause a lattice distortion that hinder the movement of dislocation. This is the effect of alloying elements with the strength to the strength. Okay, if you add nickel, okay, at the same amount of nickel, for example, 2.0, um, compared with molybdenum, manganese, copper, and silicon, you can see, okay, they produce different strength. So among these five elements, uh, silicon shows the highest yield strength. And what about phosphorus? Okay, phosphorus is forming interstitial solid solution. Unlike this one, these are substitutional, and this one in interstitial solid solution. This one is substitutional solid solution. So therefore, you can see that yeah, phosphorus, carbon, and nitrogen, the weight percentage is very low. In fact, 0 point something only, 0.5, something like that. Why? Because it is in the weight percentage, weight. So these category are very light. It is light elements. Okay, by adding up until 0.5, you can see a very significant improvement in terms of the properties. So the effect of alloying element on the corrosion resistance, how by adding the alloying element, it can lead to the reduction in the corrosion rate. Alloying elements such as chromium, uh, what happens if you add chromium? It will combine with the oxygen in the air to form a stable chromium oxide layer. that protect the base material from the outside environment. Base material is the steel structure itself. Okay, your steel structure is protected by chromium. Okay, it is like this, right? You have chromium in your steel. This is your steel. Okay, and you put chromium in your alloy. So if your steel exposed, okay, we call this stainless steel. Okay, if your stainless steel exposed to the air, what happens is it's forming chromium oxide. Okay, chromium oxide is just a thin layer, several micron layer, and what you can see from it will quickly form an oxide. So there's no chance that iron will form oxide. Without this, okay, if you're inside you have iron also. Without this, iron will form oxide, which is this is a orange like structure that you see as a rust. Correct. Rust. Okay, iron oxide is rust. But if you add chromium, chromium will react with oxygen faster. Okay, because of the in the series of electronegativity, it will easily react with the oxygen. It will react faster. There's no chance that iron will react with oxygen. So as long as you have chromium in your alloy, if you give a cut here, you give a cut, scratch or whatsoever, chromium inside your steel will quickly react with the oxygen and forming a protective layer, continuous, protective, and stable layer. Okay, it will protect your steel from corrosion. Effect of alloying elements on the eutector point. Okay, what is the eutector point? It's an isothermal reaction at a constant temperature. Alloying elements can also act on the arsenide stabilizer. So how arsenide stabilizer means that you can have arsenide at slightly lower temperature. So what happens is it's lowering down the eutector temperature and widen the temperature range over which arsenide will stable. It's like this. If you look at this, for example, you compare between molybdenum and chromium. If you have 6% of molybdenum and chromium, okay, molybdenum and chromium, all right, what is the adjustment on the eutector temperature? In normal iron carbon phase diagram, all right, this is normal iron carbon phase diagram. The eutector temperature is 7 to 3 degrees Celsius. But if you add alloying element, it will adjust this line upper or lower. Okay. Example here in this molybdenum and chromium, what happened in molybdenum? By adding 6%, you can increase the eutector temperature up until 1,000, more than 1,000 degrees Celsius. That means you will ensure that if you use your steel at higher temperature, there's no way the stable structure at room temperature will change into austenite. Okay, so again, let me show you. All right, let's say this is the original temperature. Okay, we have this original temperature without the element, which is 7 to 3 degrees Celsius. And then you add chromium. What happens is, if you add chromium, you can have something like this. This one is 1,000 degrees Celsius. Okay, all right. So arsenide will stabilize above 1,000. So whatever the application that you use, you will ensure that compared to the normal ones, the arsenide will never form at your alloy if you shift this eutector temperature higher. Okay, so you know, if you induce heat on your steel and you reach the temperature of arsenide, meaning that the original microstructure of your component will change. So if they change the microstructure, means it will change the properties. So whatever the initial design requirement that you set for the component will not be supported by your steel anymore. So make sure if you need to use your steel at higher temperature, you can choose the correct alloying element. For example, like if you want to make sure it is stable at high temperature, choose a molybdenum. All right. But if you require lower eutectic temperature, for example, like manganese, okay, instead of original one is 723, but now it becomes 700 only. So meaning that the eutectic temperature is reduced to this one, okay, 700. So you can have your arsenide phase at lower temperature. So let's say you want to make sure it's able to form arsenide phase at lower temperature. For the purpose of heat treatment, you can add manganese, and you can ensure you can have the 700 pieces arsenide phase at lower temperature. So it will help you in terms of the heat treatment process. So by having this kind of series of data, you can always tailor your steel following the requirement of your design. And another thing need to be considered is the by adjusting the carbon content and not carbon content. This one is manganese content. Okay, there are the, the lowest uh, eutectic temperature is if you add 9% manganese, and this one shows the 6.5% manganese, and this is the okay. Uh, I'm confused with this one. Oh, okay. This is the carbon percentage. Okay, different carbon percentage and the manganese percentage. So, um, right. So at this point, you can see that not just reducing, lowering down the eutectic temperature, but also widening. Okay, uh, temperature range of the austenite. So the region of austenite is wider. Okay, and for this one is limited only this region. Okay, the temperature range for the untreated not untreated unalloyed carbon steel is limited. Okay, smaller than compared to alloy containing a different range of the manganese. Okay, alloy element can also act as a ferrite former. They rise the eutectic temperature, thereby restricting the austenite field. Okay, like the molybdenum, it can by adding molybdenum, it can increase. This is what I have explained just now. So you can have a higher eutectic temperature. So what happened for the higher eutectic temperature is you can have a stabilized ferrite. Okay, so it is less chances that ferrite will transform into austenite. And besides, by adding alloying elements, it will affect the TTT diagram. Okay, one common effect that all alloy elements produce uh, is shifting the C-shaped curve toward the right. Okay, for example, this is without the alloying elements, and this one is this is a plain carbon, and this is alloy. So you will have a longer time for stable martensite. So for without for the plain carbon steel, you need to do quenching quickly so that it won't cross this line. But for the alloy steel, you can have the quenching at longer time, meaning that you can do it on the large part, large section, high volume component, without worrying that the hardness will not achieve at the core level. You can fully achieve hardness outside and inside a structure. Okay, so therefore diffusion process slow down and more time will be required for light formation. Okay, merging steel. Merging steel is a high strength alloy made with around 80% nickel and lesser amount of cobalt, molybdenum, and titanium and aluminium. It contains extremely low amount of carbon. The carbon content is kept very low to avoid the formation of titanium carbide precipitate, which severely reduce the impact strength, ductility, and toughness. Because why? The carbide, whatever you have a metal carbide, even iron carbide, they are very brittle. So that's the reason merging steel is improve this kind of impact strength. Brittle, there's no way you can have high impact strength. Okay, so this merging steel is avoid the formation of other elements with a carbide. So the heat treatment cycle to produce merging steel. Okay, starting with austenizing, and then you obtain austenite. After fully obtain austenite, you quench, and then you will get polite. The microsynthetic microstructure in as cold merging steel is soft compared to the martensite formed in the plain carbon steel by quenching. Okay, thermal aging. After several hours of fine dispersion of hard precipitate, rather than forming carbide, it forms a hard precipitate between the alloying elements such as the nickel molybdenum, nickel titanium, nickel aluminum, and iron molybdenum. Okay, there's no carbide, there's no iron carbide, there's no titanium carbide. So this carbide is a brittle. So instead of producing intermetallic of this element, we produce this kind of intermetallic, or maybe not intermetallic compound. Is some kind of alloy with a specific composition. Okay, so the precipitates in merging steel are effective at restricting the movement of dislocation. Okay, merging steel is used in aircraft with application including landing gear, okay, dekat tempat tayar tu, untuk aircraft, helicopter, undercarriage, sled track and rocket rotor case. Due to the strength, flexible, and extreme toughness, professional fencer will only compete using sword made of merging steel. So, in summary, the plain carbon steel contain, in addition to the carbon, a little only residual concentration of impurity. When the carbon content of steel is increased to above 0.3, they can be heat treated by quenching and tempering to produce high strength with reasonable ductility. Alloying elements such as nickel, chromium, molybdenum can be added to plain carbon steel to produce steel with enhanced properties. Merging steel is special kind of low carbon steel with high concentration of alloy element with high strength and excellent ductility. Okay, remember it is merging is extremely low carbon. So with a very minimum carbon, the intermetallic form uh, precipitates will only form by combining between elements other than carbon. So it is improved in terms of the impact load. Okay, I think that's all for this first part of this chapter. Let's take a break about 10 minutes and come back later at what time? Okay. The second part of this chapter is about Okay. All right. Stainless steel. Okay. I think among other steel that's being widely used in the application, uh, stainless steel is being applied so much in the application. So, however, there are different category of the stainless steel. So, by the end of this lesson, you should be able to differentiate between the type of stainless steel and describe the distinctive properties of the different types of stainless steel and cite some of the application of the different type of stainless steel. Okay. Uh, as an introduction, over time, ferrous metal, due to the nature of iron, will become corrode, okay, resulting in the formation of iron oxide, known as rust. Okay, this one I have explained just now. So the iron combined with oxide, you will see it in the form of orange-like surface. So like this one. The orange-like surface is actually a rust. It is an iron combining with the oxide, oxygen. Corrosion such as our rust, uh, it will weaken and degrade the metal on a molecular level and compromise the structural integrity of the alloy. So imagine if you have designed something to support the load. Okay, for example, you have a compression load or tension load. Okay, you have a structure like this. So the strength is the stress that experienced by this structure is stress equal to F over A. What is A? A is a cross section of this structure. So if this structure is being corroded at the surface, so the A will be changed. Okay, become A uh, final. Okay, not initial. AF. So the size will be reduced. So the stress, if this one is reduced, the stress experienced by this structure will increase, isn't it? So if you said that this structure design can support a load maximum of 600 megapascal, because of the size is changed, so meaning that the applied load stress is higher than this design limit. So meaning that your structure will fail. So that's the reason, as a corrosion engineer, they will monitor what is the thickness of the structure. If it is plate like a ship hull or any structural body, or what else? Let me think. Pressure vessel. Okay, if there is a degraded in terms of the thickness, so meaning that the structure won't be able to support the load as higher as the initial design structure. So if they monitor the dimension, it decrease in dimension, so meaning that they have to limit the load. For example, initially 600, and after a reduction of size, they need to readjust the load. So meaning that this component can be used, still can be used, but it reduced to 500 megapascal, for example. Okay, so this is what industrial practitioner trying to prolong the life of any structure by adjusting its normal use of that particular structure. So, for example, a ship, okay, they design whatever the metal part inside, if it is being welded, the welding life, the structure that being welded, it has a limit lifetime, which is 22 until 25 years old. Okay, after that, they have to scrap the ship. Imagine it is a 10-meter long or 100-meter long ship. There are a huge amount of metal parts inside, just thrown away. Okay, there's so many um, uh, this no, there's so many so huge garbage in our earth. So that's the reason they try to investigate if there is a shortage in the structure because of the corrosion. So how we can prolong the lifetime. Okay, for example, if the size is reduced, so we can increase the lifespan by modifying the applied load, something like that. So this is if the structure is being rust, corroded. So um, it will weaken and degrades the metal, molecular level, and structure integrity. So that's the reason we have to always monitor the size, dimension, thickness of our metal part, whether or not it is being degraded. All right, the stainless steel is a group of ferrous alloy that contains a minimum of approximately about 12% chromium, a composition that prevents the iron from rusting. It's quite huge. It's more than 10%, meaning that in your steel there are iron plus carbon, but now the amount of iron is reduced, okay, because it's occupied by the chromium. It is larger than 12%. So high alloy steel is dedicated for the stainless steel because alloying element is more than 10%. Okay, more than 10%, so we call it high alloy steel. So the chromium forms a surface oxide that protect the underlying ferrous alloy from corroding when being exposed to the oxidizing agent such as oxygen at an ambient atmosphere. The protective oxide layer will be produced. Okay, when we talk about the protective layer, it is just an oxide of the metal. Okay, without this chromium, we will have Fe2O3. This is also oxide, but this one is not protective. But if you have a chromium, you can have any other elements, and they also can form oxide. But the reason we choose chromium because chromium can react with oxygen faster than iron. So meaning that if in your material you have chromium, so chromium will win when there is exposure to the oxygen, and not just because of that productive or active material of chromium. Besides, when they form a layer, an oxide layer, this guy, it is a the characteristic of this layer is it is protective layer. It is passive. It is strong. It is adherent to the substrate or the base material. Unlike iron oxide, okay, iron oxide is fragile, orange light. It's not protective. It's not continuous layer. It's very porous. You can easily, rust, right? It is orange light. If you just touch the rust, it will easily peel off. Okay, but imagine stainless steel. It is a shiny light surface. The shiny light surface of stainless steel is actually the chromium oxide. What you can see, a metallic, a very shiny surface, it is actually chromium oxide. Okay, it is oxide also. Iron oxide and chromium oxide both are oxide, but they are different in terms of characteristic. One is very poor properties, one is very protective properties. So we need to choose a right alloying element to make sure that it serves the purpose. Okay, when we talk about stainless steel, there are several types of stainless steel. We have ferritic, austenitic, martensitic, duplex. If you look at the FERR, it's like a ferrite. Okay, the names is given always associated with the original condition of the steel faces. Okay, the austenite, we call it austenitic. Martensite is something associated with martensitic is associated with the martensite formation, and the duplex is combination between ferritic and austenitic. Okay, ferritic stainless steel are essentially iron chromium binary alloy containing about 12 to 30% chromium with a very low carbon content. They are called ferritic since their structure remain mostly ferritic. Okay, BCC iron at any temperature. So if you have a low carbon content for your stainless steel that having 12 until 30%, the majority of the structure having ferritic structure. Because why? Because mostly on the left side of iron carbon phase diagram is dominated by ferrite. Okay, and then this is iron chromium phase diagram. You add chromium, so you will stabilize the austenite phase or ferrite phase depending on your chromium composition. Due to the chromium content of more than 12%, this stainless steel do not undergo the FCC to BCC transformation and cool from high temperature as a solid solution of chromium in iron. They are not hardenable by heat treatment due to the low carbon content. Again, low carbon, not hardenable. In order to strengthen and harden this stainless steel, cold working. Sama je macam plain carbon steel. Okay, cold working is the preferred process if you want to increase the strength. Oops. The application for stainless steel are relatively low in cost since they do not contain nickel. They are used mainly as a general construction material in which their special corrosion and heat resistance is required. You apply this just for the corrosion resistance. Okay, and some heat resistance required. High temperature application also can be can use this kind of ferritic stainless steel. High temperature applications such as heater, combustion chamber. Okay, um, also it be used for the exhaust material. So you can use ferritic stainless steel. Authentic stainless steel are essential iron, chromium, nickel ternary alloy that containing about 60 to 25% chromium and 7 to 20% nickel. So if you want to have the stabilized austenitic phase, you need to add nickel. Okay, these alloys are called austenitic since their structure remain austenite phase, which is having FCC at all temperature. Okay, the austenite consists of single phase austenite iron type solid solution. So this the presence of nickel which has an FCC. Okay, why it have FCC? Because it has a nickel structure enable the FCC structure to be retained at the room temperature. FCC structure of the steel can be retained at room temperature because the nature structure of nickel, which is also FCC. The austenitic stainless steel have a high amount of austenite, which make them mostly non-magnetic. Okay, unlike the ferritic stainless steel, austenitic stainless steel is non-magnetic. Okay, this stainless steel also has a low percentage of carbon, and therefore it cannot be hardened. So when we talk about low carbon, okay, cannot be hardened. Okay, if you, how to make it increase in hardness? So you need to conduct cold working process. The high formability of austenitic stainless steel is due to the FCC. Okay, and these steel are the most popular grades of stainless steel produced due to the excellent formability. Okay, senang. It is easy for you to turn it into any shape and to apply for any application. Multi-seated stainless steel are essentially iron carbon containing between 12 until 17 chromium with the the carbon content between 0.15 to 1%, with the percentage of carbon martensitic microstructure can be produced by quenching from the austenitic phase region. So it is up until 1% carbon. So if you look at the percentage of carbon, we know that between 0.6 until 1.4 is high carbon steel, isn't it? So for the stainless steel up until 1%, with the addition to the chromium between 12 to 70%, you can have the martensitic phase in the stainless steel. So the martensitic stainless steel with tempered martensite microstructure has a good hardness plus toughness, and they have been used largely for medical tools. So uh, above all, they are all for the different properties. If you have ferrite, if you have FCC austenite, they are different in terms of the strength. And for martensite, they have a high hardness plus the toughness, similar to the plain carbon. But the thing is, it is stainless steel. It is high corrosion resistant. You need to avoid corrosion in this kind of application. For example, medical tools. Okay, takkan you nak pakai benda yang berkarat kan? So it is not safe for the medical tools. You need to ensure it is a high corrosion resistant. Kitchenware, kitchen utensil. Takkan you pakai sudu yang berkarat. It is almost impossible. All the spoon and uh, whatever the kitchen utensil, they must not corrode. Otherwise, you will poison your food. Or yeah, because you know how the nature of this kitchenware is being used, right? It's quite a frequent use. General purpose heat treatable, such as the machine parts, pump, shaft, ball bearing, racers, valve part. And last category of stainless steel is duplex stainless steel. What is duplex? Duplex stainless steel have a two phases microstructure consisting ferritic and austenitic stainless steel. It's combined. Okay, BCC and FCC. So the combination of these uh, phases will combine also the property between these two um, category of stainless steel. Okay, in this category, duplex stainless steel is contain chromium between 90 to 32 and molybdenum. Okay, molybdenum um up to 5% than the austenitic stainless steel. So meaning that whatever the austenitic stainless steel that you have, you add more alloying element, which is a new alloying element, which is molybdenum, but significantly less nickel. So the application of duplex stainless steel are about twice as strong as regular austenitic or ferritic stainless steel. They possess better toughness and ductility. Ductility associated with the austenitic stainless steel because of the FCC structure. Okay, but not as excellent as austenitic, of course, because it has some portion of ferritic structure. So duplex stainless steel find application in the manufacturing of chemical, petrochemical, oil, and gas product that is post-process equipment to highly corrosive fluids. So in short, the stainless steel are steel alloy with a minimum chromium content of 12% and up until 1% of carbon content. Chromium is added to steel to increase its resistance to oxidation or corrosion. Stainless steels are classified according to the main microstructural constituent. The four classes are ferritic, austenitic, metastatic, and duplex. I think that's all. If you, I think that's all for this topic. We have only two lessons for this module, and for the next class in Wednesday, I think we can skip the class. We will proceed on the Tuesday. Okay, so you have any question? So on Tuesday we are going to discuss on the assignment. If you have anything, you can ask during the tutorial class. So any question?
Doktor, untuk test tu apa masuk?
Dia akan masuk sampai modul 7.
Dari 1 sampai 7?
No. Dari 5 sampai 7. This is mechanical properties. This is heat treatment. Iron steel. Iron carbon. Iron carbon phase diagram and heat treatment. Okay, 5, 6, 7. And we have not yet discussed the form of test because we need to analyze the result for the test one and see the performance of student. I think some of the lecturer has not yet finished marking your test one.
Ni open-ended juga, Doktor?
Tak discuss lagi. Kena analyze dulu your punya result performance and decide whether we are going to do the same method for test 2. Boleh? Nanti dah ada nanti saya beritahu lah.
Okay, thank you.
Nanti saya beritahu. Hari Khamis nanti saya beritahu. Ke hari Ahad. Okay. I think that's all. For those who has not yet scan your attendance, please sign attendance. And for those who has